Welcome to the session on outdoor propagation model. Outdoor propagation model involves in the estimation of propagation loss over irregular terrains. So outdoor propagation model, it is for estimating the loss in irregular terrains. Okay, so based on the coverage area, the outdoor propagation environment is divided into three categories. First one is the propagation in macrocells, microcells, and then in street microcells. So here is the comparison between microcells and macrocells. So the cell radius for macrocell is around 1 to 20 kilometer, and for the microcell it is 0.1 to 1 kilometer. And the transmitter power for the macrocell is around 1 to 10 watt, and for the microcell it is 0.1 to 1 watt. And the fading technique used in macrocell is Rayleigh, and in microcell it is Nakagami. And RMS delay spread for the macrocell it is 0.1 to 10 microsecond, and for the microcell it is 10 to 100 nanosecond. And the maximum bit rate for the macrocell is 0.3 megabits per second, and for the microcell it is 1 megabits per second. Yeah. And coming to the models, outdoor propagation model or radio propagation model, it is generally classified like empirical model, analytical model, and numerical model. So empirical model is based on the data collected from real-time measurements, and the analytical model is based on mathematical equations, and numerical model is it uses the computational techniques to simulate the behavior of your radio signal. Okay, so generally the outdoor propagation model is to estimate the propagation loss over irregular terrains such as mountain region or a simple curved earth profile, right? Okay, so the terrain profiles taken into account for predicting the path loss. So based on the systematic interpretation of the measured data obtained in specific area, your path loss is calculated. Okay. So these are all some of the empirical models. As I said, empirical model is based on data collected from real-time measurements. So this is your empirical models. So Okumura model, Hata model, Longerais model. So these are all some of the examples for your empirical models. So first, today's class will discuss about Okumura model. Okay, so Okumura model is widely used for signal prediction in urban areas. As I said, the outdoor propagation model is considering the irregular terrain profile. Okay, and for example, like the tree, buildings, mountain regions, and so on. So some commonly used outdoor propagation model is the Longerais model, Okumura model, and Hata model. So now coming to the Okumura model. So Okumura model is a widely used signal prediction model for the urban areas. Okay. So in 1968, Okumura did a lot of measurements and produced a new model. So as I said, the empirical model is based on data collected from real measurements. Okay. And this model is used for signal prediction in urban areas. It is widely used for the urban areas. So Okumura introduced a graphical method to predict the median attenuation related to free space for the quasi-smooth terrain. So this graphical method model contains of set of curves which is developed from the measurements, and it is valid for particular set of system parameters in terms of carrier frequency, antenna height, and etc. So Okumura model, as we said here, the parameters are carrier frequency, antenna height, and so on. So this Okumura model is used for the frequency around 150 megahertz to 1920 megahertz frequency range from 150 megahertz to 1920 megahertz, and for the distance of 1 to 100 kilometer. and it is used for the base station height of about 30 to 1000 meter. So this is the height of the antenna, base station antenna, and this is your distance. First of all, the model determined the free space path loss of the link. After the free space path loss has been computed, the median attenuation is calculated from the Okumura's curves. Okay, so the model is designed for the frequency range of 150 MHz to 1920 MHz and mostly used for urban areas. So Okumura model assumes the path loss between your transmitter and the receiver in a terrestrial propagation environment, and it is expressed by this equation. So we are finding the median loss. Okay, so for finding this median loss, first we have to find out the free space loss. Okay, and the attenuation, your transmitting antenna gain, receiving antenna gain, and the area. So this is the formula. So these median attenuation gain, these median attenuation and this gain due to the environment, this is all calculated using the Okumura's graph curves, right? So it is called as this AMU, it is called as median attenuation relative to free space, or it is a correction factor to account of the terrain. Okay. So this attenuation and the G area has been plotted for wide range of frequencies. What is the frequency range? From 150 megahertz to 1920 megahertz. So generally we use it for 200 to 1920 megahertz. So antenna gain varies at the rate of 20 dB or 10 dB per decade. So your antenna height, transmitting antenna height is, a gain of the transmitting antenna height is given like 20 log HTE by 200. For the HTE ranges from 10 meter to 1000 meter, and your receiving antenna gain, it is given as 10 log HRE by 3. Your receiving antenna height ranges, it is less than 3 meter. So for a receiving antenna height less than 3 meter, we have to use this formula to calculate the gain of the receiving antenna height. And the gain of receiving antenna height, if your antenna height is between 3 meter to 10 meter, then it is 20 log HRE by 3. And del H is the terrain undulation height, isolated rigid height, average terrain slope, and it is and mixed land sea parameters. So see here, from this graph we can calculate your attenuation relative to free space. So for example, if it is 500 megahertz, so 500 megahertz, and the distance is 50 kilometer, let us assume like that. So 500, we'll just draw a rough line. So for 500 and for 50, so in this 50 kilometer curve, where does it cross? So this is the point. So if you see here, it is around 35 dB. That is your attenuation related to free space. And for calculating the correction factor, that is G area, so for given frequency and for the area, suburban or quasi area or open area, we can calculate the correction factor. So for example, same 500 megahertz for the suburban area, if I see, what is the correction factor? It is around 6 or 7. Next is the Hata model. So before going into the Hata model, we can see what is the advantage of your Okumura model, merits and demerits of your Okumura model. So Okumura model is the simplest one and the best in accuracy in the path loss prediction for cellular and land mobile radio system. Okay, and very practical, and it is used in modern land mobile radio system. And coming to the demerit, it is having the slow response to rapid change in your terrain. Okay, hence it is fairly good for your urban and suburban area, but not for the rural areas. That is why Okumura model is used only in the urban areas. Okay, widely used only in urban areas because it is having a slow response to your rapid change in the terrain. Okay, and the standard deviation between the predicted and the measured path loss is around 10 dB to 14 dB. So that is the drawback of your Okumura model. Otherwise, Okumura model is a simple and best in accuracy. Right. So next is your Hata model. So Hata model is also one of the empirical model. So what is empirical model? Empirical model is based on data collected from measurements. That is your real-time measurements. Right. What is analytical model? Analytical model is based on the mathematical equation, and numerical model is based on the computation techniques to simulate the behavior of your radio signal. Okay, right. So Okumura model is widely used for signal prediction in the urban areas. What is the frequency range for your Okumura model? It is 200 megahertz to 1920 megahertz, and the distance is for 1 to 100 kilometer, and your antenna height is from 30 to 1000 meter. Now Hata model. Hata model is also an empirical model, right? It is mostly widely used model in the radio frequency. It is going to predict the behavior of a cellular communication in built up areas. Okay, so this is an empirical formula for propagation laws. It is derived from Okumura's test. Okay, this Hata model is derived from the Okumura's test in order to put the prediction method to computational use. Okay, so it is applicable to the transmission inside the cities and suited for point to point and broadcast transmission. And the frequency range here is 150 megahertz to 1.5 gigahertz, and the transmission height is up to 200 meter, and the distance is less than 20 kilometer. Okay, so could you pause the video and just tell what is the major difference between your Okumura model and your Hata model? So Okumura model, the frequency range is from 200 to 1920 megahertz, whereas here it is 150 megahertz to 1.5 gigahertz, and the distance there was 1 to 100 kilometer. Here it is 200 meter. Sorry, the distance is 20 kilometer, and the antenna height there was 32,000 meter, and here it is 200 meter. Okay, so Hata transformed Okumura's graphical model into an analytical framework, and hence he has given the formula for Hata model as follows for the urban area. So this is that. So what is FC? FC is your frequency operating frequency, HD antenna transmitting antenna height, HR is the receiving antenna height, and the distance. Okay, so we are finding the median loss. Okay, so your receiving antenna height ranges between 1 meter to 10 meter, and your transmitting antenna height ranges between 30 meter to 200 meter, and the distance ranges from 1 to 20 kilometer. Okay. And AHR, this is the correction factor, whereas there your G area was the correction factor. Okay. So area is a correction factor for mobile antenna height HR for a small or medium sized city. Okay, for a small or medium sized city, your correction factor formula is this: 1.1 log FC minus 0.7 into HR minus 1.5 log FC minus 0.8 dB. And for the large city, the correction factor for the mobile antenna height HR is this. And this also again classified like for frequency less than 300 megahertz, we have to use this formula. And for the frequency greater than 300 megahertz, it is this formula. So to obtain the path loss for the suburban area, the standard Hata model is modified like for the urban minus this. Okay, and for the rural area, it is L50 urban minus this calculation. So it is actually derived from the Okumura model. Okay, transformed Okumura's graphical model into an analytical framework. So that is your Hata model. Right? So we'll stop with this. Next class we'll discuss about the remaining empirical models and so on. Thank you.